Hi, I'm Bren, and I made this video to demonstrate text classification for first-time and beginner users of a data mining program called Weka. These are from a popular data set for studying text classification. Most of what you'll see in this beginner-friendly tutorial applies to working with text data in particular. When you're using text data in Weka, you can do this with text or that with text. Some of what you'll see applies to working with text and other data types too. The dataset was shared by the Cornell Natural Language Processing Group in New York, whose machine learning based NLP work is well known and impressive. It's 2,000 movie reviews from IMDb, 1,000 positive, 1,000 negative. They're labeled for supervised machine learning, and in Weka we're going to start training classifiers how to predict the sentiment of each document. That is, if the 2001st movie review were written tomorrow, could the machine learning classifier automatically and accurately label the document as positive or negative? Furthermore, if the 2001st movie review was written next month, has the classifier discovered on its own new and improved features to make its prediction better? This is Weka, an open source data analysis program shared by the machine learning group at the University of Waikato in New Zealand. Weka is also a classic repository of machine learning algorithms. Machine learning is a type of data analysis for building artificial intelligence. There's usually a database you'll want to apply machine learning methods to for discovering valuable knowledge. This text classification in Weka tutorial has 5 sections. In the first section, you'll see how this one line of code, the text directory loader script, without knowing any programming, turns those 2,000 text files into an ARF file so we can use it in Weka. In the second section, you'll see each setting in the string-to-word vector filter. Text in the 2,000 movie reviews will get imported to Weka as string text data. String is a data type machine learning classifiers usually cannot process. You'll see a variety of ways string-to-word vector converts string data to numeric and nominal data, which learning algorithms will process, and sometimes they can do it well enough they're referred to as expert and intelligent systems. Each of the string-to-word vector settings are ways you choose how to represent each movie review as a document vector. We'll see how in machine learning you make these choices with the goal of creating effective feature vectors. We'll change these values to see the results of various settings, such as word presence, word frequency, tokenizers, TF-IDF ranking, stemming, stop words, and more. Sections 1 and 2 are text analysis specific sections. After using these first two tools in Weka, once we're in the third section, the values we'll be working with will all be numbers and categories, and at that point many subsequent tools in Weka you'll see are useful for text classification, and additionally useful working on other types of data analysis as well. In the third section, you'll see why the attribute select filter and string-to-word vector are frequently used together. Attribute select settings are ways to evaluate and rank the predictive quality of what's in your feature vector. After transforming the text into a more machine-friendly dataset with string-to-word vector, we'll reduce the dataset with attribute select as a technique to improve classifier performance. In the fourth section, since this is a beginner-friendly tutorial, addressing 2 common problems will be briefly demonstrated that are commonly applied in classification. In the fourth section, first we'll see an example of cost-effectiveness learning in Weka, using an algorithmic approach that can tell the classifier what the more costly mistake is, specifically telling the classifier to be 10 times more careful with false positives than false negatives. In the fourth section, second we'll see a couple of sampling techniques to adjust for class imbalance. Many times you'll be asked to predict something but have many more of one outcome than another outcome. For example, you'll have only 100 examples of patients with a disease, but 5,000 examples of similar patients without the disease. To build a better classifier, you may oversample the minority class and or undersample the majority class. We'll see an example of each sampling technique in Weka. In the fifth section, we'll see 6 different classifiers that are popular in text classification: naive Bayes, multinomial naive Bayes, k-nearest neighbor, J48, random forest, and support vector machine. For each I'll provide a big picture explanation so beginners can conceptually distinguish how each uniquely processes data. How J48 is based on entropy. Naive Bayes assumes attribute independence. Just basics like that, I don't go deep into math or theory. You'll see how to change a setting or two for each classifier, such as where to select Euclidean, Manhattan, or another distance as the distance function that defines a nearest neighbor, and what changing k equals 1 to k equals 5 to k equals 9 means. It's not a comprehensive list of text classifiers, but hopefully it makes machine learning with Weka easier and faster for you. Most of the classifiers are not only popular in text classification, they're popular for many other types of data analysis as well. Section 1. Text Directory Loader. This short line of code will turn our 2000 movie reviews into a single file so it opens in Weka. Look at the left. Imagine 2000 web pages with an IMDb movie review. Cornell NLP Group got us going. They removed HTML from each review, lowercase the text. Looking at the left, you'll see they turned each sentence into a separate line. They cleaned them up to give us these starting point text files. Reviewers classified, aka categorized, their own reviews by submitting them with a grade, such as a 5-star system where 3.5 stars and up are positive, 2 stars and below are negative. Let's easily import the 1000 documents in the positive folder and the 1000 documents in the negative folder in one swoop with Text Directory Loader. It's 2 steps. First, I find the main folder with the documents. Second, I save it to my laptop. I could just type this, and it saves in the default Weka folder. I'll save it elsewhere, in Weka's data folder. And in under 30 seconds, the 2000 documents are turned into one R file. The 2000 documents and labels are contained in the R file. This is the R file format to use Weka. CSV files can be used in Weka as well, but I used ARF because in Weka, ARF is less memory intensive, faster, and better for analysis because it includes metadata about column headers. Movie reviews are in the data section, represented as 2 columns. The attributes section are columns, and we not only will add many more columns, we will try representing them in Boolean, real numbers, single words, phrases, and otherwise to find a configuration or two that learning classifiers perform the best with. It wouldn't perform well if we left the text in each movie review as a mere string text value. Is text in a movie review a number value? No. Well, not yet. Is text in a movie review a categorical value? No. Well, not yet. Is text in a movie review a date value? No, at this point text in a movie review is just random text. Text Directory Loader simply got us started by importing the documents and using which subfolder they were in to retain positive and negative categories. Text Directory Loader also saves us time as it added some syntax to be Weka compatible. String values now end and start with single quotes. Apostrophes now have a slash in front of them. Now using Weka's string to word vector, we'll be ready to transform the random text into document vectors, which is our opening move in a game called Feature Selection. Section 2. String to word vector. Let's vectorize all 2000 documents. Think of a spreadsheet. Documents as rows, words as columns, values as numbers. That's right, numbers to represent text. These, formerly known as IMDb movie reviews, are now more aptly named document vectors, and in this tutorial it's how we'll feed a movie review to a classifier. Each vector and its training features are designed for a learning classifier to become an expert at distinguishing positive reviews from negative reviews. Being a good teacher and finding the right training features for this particular task is a journey that begins right here with the settings you see in string to word vector. We're using Weka's GUI, allowing us to not use Java, which is what this actually is. Imagine lines of code in Java, and each of these settings is part of that script. When you click apply, you run the script on this, which contains the text in all 2000 movie reviews. The text will change to a different form, one that makes sense to these classifiers. We now have 2000 movie reviews, but goodbye string value that the classifiers couldn't understand, and hello 1165 characters and words as number values, plus this categorical attribute that labels each document as positive or negative. These attributes all are features we've extracted from the original dataset. We've begun creating a new and more machine-friendly dataset. In Weka, we put what we're predicting at the end. Easy way to change it is click Edit. The last and class attribute is what you're predicting. Learning classifiers have ways of learning how everything else can be used as predictive features. Then it makes its initial predictive model, and later when you feed classifiers more of the same data, it remodels the prediction and improves over time. These settings are different ways of feeding data to a machine learning classifier, ways of representing each movie review as a document vector, and I'll summarize each individually. Words to keep. I may set this to a very large number, in this case a 6-digit number, so every word is kept. The default's 1,000. Let's assume most words won't be valuable. I want it to run faster, and lower it to 100. This is going to pick 100 words per class. That is 100 words from the positive reviews and 100 words from the negative reviews. There's typically a little overlap. We've set it so less words are kept. The string attribute has been converted into 112 numeric attributes. With the class attribute, it totals 113. As we scroll down and look at the bottom right, word frequencies, we see words about, after, all, also, which frequently occur in one or each class. In document 1, did the words about, after, and all appear? Yes, yes, yes. In document 2, did about, after, and all appear? No, no, yes. The presence or absence of a word in a document is one of many clues a movie review sentiment algorithm can use to make its prediction. Let's see another. Output word count. Instead of values that tell a classifier if a word is in a document, changing this setting to true will create values that tell a classifier how many times a word is in a document. Instead of values indicating word presence, Boolean, turning output word count creates values indicating word frequency, a real number. Do not operate on a per class basis. We set words to keep to 100 before, and it kept 112 words because we looked both for 100 words in the positive reviews and 100 words in the negative reviews. The reason it didn't create exactly 100 is some words have the same word count in each class, and it looks for 100 words with different word counts in each class, which is helpful to compare why each class is different. Imagine this time we're set on 100 words. We can change do not operate on a per class basis to true, and the 101st is just a label. It created 100 words this time. IDF transform and TF transform. TF-IDF is a way to find words and documents that are strongly related. Words and documents that are very relevant to each other. If the word super appears in 3 of 2,000 documents, that's low document frequency. Which of the 3 documents is super most related to? If super appears 100, 5, and 2 times in the 3 documents, super has high term frequency in the document it's in 100 times, and a very high TF-IDF ranking. Think about that combination, high term frequency and low document frequency. Words that rarely appear in the document collection and frequently appear in particular documents. TF is term frequency, high term frequency is good. IDF is the inverse of the document frequency value, which is why I've been saying low document frequency is good. The DF value is flipped upside down in the formula, which is TF times IDF. To use this informative statistic in Weka, turn output word count on. If it's turned off, there's no TF. TF-IDF needs to know how often a term is in a document, not if a term is in a document. The value of words is their TF-IDF score this time. This word may be especially relevant in these specific documents. Normalized doc length. Normalization, in the statistics sense, refers to measurements taken on different scales and remeasuring them on a common scale. How often a word is in a document can be measured not simply by how often a word is in a document. It could then be remeasured based on document length. If you're examining word frequency of funny in the document collection, after being normalized by document length, there are different values. If funny appears 3 times in a short and average sized document, the value of funny will be more in the short document. This is a before and after. Document 7 is highlighted. Document 1 is on top. And this word appears the same amount of times in documents 1 and 7. This is document 1, 802 words. This word appears once in this 802 word document. This is document 7, 1,178 words. This word appears once in this 1,178 word document. They had the same word frequency value in the original data set. Normalization said, but they were taken from different sized documents, so I'll remeasure it. And in the new data set, all the words in document 1 go up a certain amount. All the words in document 7 go up a certain amount. But that certain amount is more for document 1. A word has less effect in a larger document. So with this measurement, the word would have to be used more in document 7 to equal the word's frequency value in document 1. Stemmers. These are stemming algorithms. Lovin stemmers and Porter stemmers being two popular types. Stemming, you already know, tries to use words better by breaking them down into a smaller form called a stem. To do this, it can inspect both sides of a word to try to remove letters from either side. Typically, it removes from the suffix side. Let's see stemming in Weka, since this default null stemmer, as it sounds, doesn't do any stemming. I'll briefly explain what a word stem is and what it is not. A word stem is not necessarily a linguistically valid word. After stemming, the word have may lose the E at the end. So HAV is the word stem, storing a set of words with the exact same letters. A similar technique you'll see in natural language processing breaks words down to a smaller form called the word lemma. Unlike the stem, the lemma is always a linguistically valid word, something you'd find in the dictionary to store a set of words with the same meaning. Unlike the stem, they do not have to have the same letters. Think and thinking may be represented with the same lemma as the word thought. The word car may be grouped with the word automobile. You'll hear lemmatization, it's sometimes useful. Stop words. When you have a document collection, such as 2,000 movie reviews, the words that appear the most, as is, and individually, many tend, and I stress tend, to be irrelevant for classification. So a stop word list is sometimes used which excludes them. At, is, and other such words, however, are relevant to phrases. That is, they group words together in relevant ways, so when using stop words, that's your balancing act. String to word vector by default uses an English language stop words list in Weka. Here's what a German language stop words list may look like. An Italian language stop words list. Spanish stop words list. Each has one stop word per line, the format of Weka's stop word lists. In a second, I'll demonstrate using a custom stop word list in Weka, so I'll save this to my laptop. This is the English stop words list that Weka uses by default. Weka is a program on my computer. Everything's in one folder called Weka, and it contains many folders and files, but there's not a stop words file to manually edit. By default, Weka just points to that publicly shared stop list online. To modify a custom stop words file, I'd make sure it's one stop word per line. This is. If I don't want a word here, I delete it or put a pound sign in front of it. If I want a word that's not there, I add it. Say a multi-language stop words file is necessary, I can paste multiple language stop words files into this. Let's add the words film and character. Then in Weka, change the stop words folder to the custom stop words file. Make sure stop words is turned on. Attributes for the words film and character would have been created by default, but being in the custom stop words list, they are not. Tokenizer. These algorithms have different ways of splitting up the text in the movie reviews. Split into tokens. What's the n-gram tokenizer? Here's the deal with n-gram. Finding potentially predictive unigrams, bigrams, trigrams, 5grams, whatever. It's first about the unit of measurement. We've been focusing on words as the unit. But single characters can be the unit, like genetic text data. Instead of a word being a unit, A could be a unit, C could be a unit, G could be a unit, T could be a unit. With proteomic text data, each amino acid can be represented as a 3-letter unit. GLU could be a unit, LYS could be a unit, TRP could be a unit. When you hear the word token, think unit of measurement. When you see the word gram, think unit of measurement. And what distinguishes unigrams from bigrams from trigrams is proximity. Words before and after other words. Letters before and after other letters. Context. N-gram tokenizer in Weka by default tries to find predictive single word units. predictive 2-word units, and predictive 3-word units. Using n-gram tokenizer, there are now words and phrases. There are no trigrams though. Even though it considered trigrams by default, none were kept. Let's run again with stemming and stop words this time. And with these settings, a trigram was kept. If you set both to 2, all tokens would be bigrams. If you set both to 3, all tokens would be trigrams. Alphabetic tokenizer is a different way of splitting up the text. In this case, because words are the unit, it says when you create words, only create words containing letters in the alphabet. With the default word tokenizer, some tokens contained an @ ampersand, asterisk, hyphen, double hyphens, whereas using alphabetic tokenizer, we wouldn't see any of those in any of the tokens, as the rule is every token must be 100% letters in the alphabet. Alphabetic tokenizer would have made unigrams only, unlike the unigrams and phrases we saw before with n-gram tokenizer. Minimum term frequency. By default, any of the over 47,000 words in the 2000 reviews is fair game. I can try 2 and 3 here to see which works better, and that would mean that words would have to appear twice or 3 times to be considered as attributes. Periodic pruning. This setting changes when count pruning is done. Here prune simply removes low frequency words. You've already seen count pruning since count pruning happened here. Periodic pruning is here if you're working with large data sets and computer memory may be incapable of pruning the large data set all at once at the end, which happens by default. If that's the case, maybe we'd set here to prune in 5 stages, do a fifth of the count pruning 20% into it, do the second fifth of the count pruning 40% into it, 60%, 80%. It would be less taxing on computer memory to periodically prune in stages. Attribute name prefix. This changes attribute names for organization. Here I prefix string attribute names with imdb:. Maybe I'm combining R files later. Lowercase tokens. These movie reviews were already lowercased. Here's an R file I made. Pretend there are 4 documents. The second document has the word more with a capital M. The third document has the word more with a lowercase m. I will leave the lowercase token setting off. Let's turn lowercase tokens on. And you'll see that the lowercase more is here. The uppercase more is not. More is now in the second and third documents counted as one attribute regardless of lower and uppercase letters. While lowercasing is a common technique, the setting is here for a good reason. Consider trying to extract someone's name from an information retrieval system. Her name is Hope, and you'd like to study the uppercase Hopes and lowercase Hopes separately. Attribute indices. This is for string attributes you want Weka to leave that way. Let's see an example. This data says 4 attributes, the first 3 being strings of text, 4th labels, instances, dumb, dumber, and dumbest. Attributes are comma separated. You'll see the first attribute of each instance includes a distinct. The second attribute of each instance includes a unique. I'm going to select attribute 1, which tells Weka just use the first attribute of each instance. Do not use all 3 string attributes. And here is the second attribute left as is. Here is the third attribute left as is. These words are all from the first attribute. Again, the first attribute all had distinct, all the second attribute had unique, and you'll see distincts from the first attribute but not uniques from the second attribute. The uniques were left here. Look at the second instance. The third part has the words uno and mas. Were they included? No, all the words from all these third attributes were left here. and not made into attributes, left as string data. So for attributes 2 and 3, attribute indices was like a string not to word vector setting. Look at the first instance. The first part has the word demonstrating. Will it be turned into an attribute? Yes, as we set it to. All the words in these first parts were included. Now if we count the first part words, instance 1 has 1, 2, 2 words, instance 2 has 1, 2, 2 words, instance 3 has 1, 2, 2 words, instance 4 has 1, 2, 2 words, that's 8 words. More is in both the second and third. And since the lowercase setting is on, attribute indices created 7 unique attributes. In section 2, you've seen there are many ways to change string data with the string-to-word vector in Weaka. To summarize briefly before section 3, in document classification, each word, each phrase, each character can be represented as a feature of an IMDb movie review. A feature is a measurable property about each IMDb movie review. Why do we change sequences of text into attributes with number and categorical values? Why do we vectorize the string data? Why do we try different data sets in hopes of finding the best feature vector for a learning classifier? Text directory loader and string-to-word vector were what? Our opening moves in designing training features. Evaluating the predictive nature of attributes we made in sections 1 and 2 is what we'll see in part 3, the attribute select filter. The attribute selection filter often complements the string-to-word vector as you create high-quality input data for Weka's classifiers. String-to-word vector changed 2,000 movie reviews and there are over 47,000 different words into 2,000 document vectors. Attribute selection is different. Although you're still making decisions about your data set, you're no longer changing its properties. No more changing characters to different 0s and 1s and 45.2s and negative 1.4s. Now it's simply time to get picky about the different 0s, 1s, 45.2s, and negative 1.4s we turn the characters into. We hope learning algorithms can effectively use some of the attributes as predictive features of movie review sentiment. Let's put that hope to the test. Let's rank the attributes and further improve the input data. For demonstration purposes, first we'll go directly from string-to-word vector to a classifier. Here, Sport Vector Classifier will build an initial model for categorizing reviews by sentiment. Setting 5-fold cross-validation makes its prediction a little more realistic. And 81.5% are accurately classified. 81% of the positive reviews and 82% of the negative reviews. Now we'll use the attribute selection filter as a middleman. These are judges. The predictive quality of every attribute is about to stand trial. Judge InfoGain attribute eval will use your style of ranking attributes. These consult with the judge and make the final decision, which are accepted and rejected. Let's pick ranker. The predictive quality of all 1,165 words, less the label, are being reviewed. 312 passed the test. Here attributes are ranked in order. Bad is ranked number 1, and is ranked number 2. Worst, stupid, boring, waste, ridiculous. Finally, a 14 is great, and some complimentary words. Let's see why bad topped the list of predictive features. Look at the bottom right. It's a word frequency distribution with blue and red bars. These are the 2,000 documents. 1,000 are blue. Blue are positive reviews. 1,000 are red. Red are negative reviews. The bottom right shows the word bad is present in over 750 movie reviews. The highest bar all the way on the left are movie reviews where bad is absent and appears 0 times. 1,239 reviews to be exact. In one review, bad appeared 11 times, so it goes all the way up to 11. The bars on the right for 9, 8, and 7 are so small they're numbers. 2 reviews had 9 bads. 3 reviews had 8 bads. 5 reviews had 7 bads. In 456 of the reviews, nearly 23%, the word bad appeared once and only once. The bar is slightly more red, 60% or so, which is not a great signal. In 158 reviews, the word bad appeared twice, and it's around 80% red. Now we're getting somewhere. 3 to 6 totals 136 reviews, and it's almost all red, around 95% red. That is, a review with 3 to 6 bads is a good signal for sentiment. How often the word bad appears can be used as a predictive feature. Why is and ranked second? Its connotation is neither positive nor negative. Starting here at word frequency 29, these 230 reviews where and appeared 29 times or more are almost all blue. It's nearly 1 in every 9 reviews. Perhaps longer reviews tend to be positive. I've never looked closely at this data, but if I were, after seeing this, I'd consider the frequency of the word and a predictive feature of reviews. Worst is absent in most reviews, so why is it ranked so high? The reviews it is in, roughly 11%, almost always are red and negative. Same with stupid. It's in roughly 9% of the reviews, which are almost always negative. Here's another one of those highly ranked neutral words, but where it's used 27 times or more, which is roughly 9% of the reviews, it's almost always blue and positive. Maybe this is revealing a pattern with neutral words. Boring looks nearly identical to worst. The word great is almost always in a positive review, and in 7% of the reviews. You get the idea. Now we have a ranked list of 311 words from the reviews, and we're getting familiar with the data. Why is the last word try even on the list? It's underwhelming in comparison to words like bad. It's here because it met the threshold, and albeit small, the word try does have positive information gain. Let's see our reduced feature vector, only 311 attributes, given to the classifier to see how well it can predict the 312th. It had 81.5% accuracy directly from string to word vector when it used 1,165 attributes, 86.25% this time. 86% of the positive reviews, 86.5% of the negative reviews. This filter can be so helpful, extracting information not only from natural language text but other types of data as well, that Weka gives it its own tab. Just a more visible place to do the same thing. In this view, let's use attribute select again. Instead of visualizing frequency distribution, we see the numeric rankings from InfoGain attribute eval. Here are the rankings of all 311 words that passed the test. The other 855 words were also evaluated, yet failed the test and aren't shown. 3 have information gain exceeding 0.04. Bad was 0.0635, and was 0.0463. Worst was 0.0422. 855 attributes had negative information gain. Remember I changed this threshold setting to 0 before? That sets the desired amount of information gain. Let's get real picky this time and change threshold to 0.04. Additionally, let's only rank a subset of attributes. In start set, if we put 1 to 800 here, we say start evaluating at the 801st attribute. Skip the first 800 attributes. We set the evaluator to rank just the last 365 attributes, specifically 364 words. The classed attribute won't be evaluated. Now it only gave us the word worst, which is based on our settings. The words bad and were in the first 800 attributes, and not evaluated. Of the last 365 attributes, everything but worst is below 0.04 information gain. Here's another way to see that the word frequency of worst in a document is a predictive feature. This is just a starting point. The x-axis has positive and negative. The y-axis shows word frequency horizontally. In positive reviews, worst is present twice, once, or not at all. In negative reviews, worst is present 6 times, 4 times, 3 times, 2 times, 1 time, or not at all. Jitter is about overlap. Most of these x's are similar overlapping values. Let's see. This starts to tell a story. Reviews where worst appears twice at this point and above just piqued my interest. This is roughly 1,000 of the 2,000 reviews, and a twist. Even where worst appears just once, it's predominantly negative reviews. Before we viewed this with red and blue bars. In this view, an easy thing you can do is subset outliers. This is when the word worst appears 3 times or more in a review. And this is the first review. I'm looking at it because it's a feature that attribute select suggests will be useful in the predictive model. If this sample data is the basis for the rule, if a review has the word worst in it 3 or more times, label it as a negative review, it would have near perfect precision. In 99 out of every 100 reviews, however, the word worst appears 2 times or less. I want to choose many more features in addition to word frequency of worst, of course. Choosing a reduced set of high-quality training features will simplify the model and improve many classifiers. Attribute select, shown here in the 3rd section of this tutorial, is one of the tools you'll use in Weka often and productively. We've now used text directory loader, string to word vector, and attribute select on our way to feeding high-quality input data to learning classifiers for predictive modeling. Before section 5, where we'll see popular classifiers in Weka for text classification, I included a section 4 as a beginner-friendly introduction to 2 fundamental data analysis concepts. Section 4 shows examples of cost-sensitiveness learning and class imbalance in Weka. Here's 2 types of correct guesses: true positives, true negatives. Here's 2 types of incorrect guesses: false positives, false negatives. Either type of correct guess typically has a cost. Alternatively, the 2 types of incorrect guesses regularly have different costs. Imagine building a classifier to diagnose terminal illness that inevitably will make 2 types of mistakes. Imagine this type of mistake has 10 times more consequence than this type of mistake. One technique for cost-sensitive learning in Weka uses the algorithmic approach. Cost-sensitive classifier is a meta-classifier. It improves a base classifier. We of course hope doesn't make many costly guesses, but when it does, cost-sensitive classifier warns the base classifier about costly guesses, and the base classifier builds a model accordingly. Say we're classifying using J48. We click Cost Matrix, change it to 2 classes, and assign mistakes in this class 10 times more cost than mistakes in the other class. That's adjusting for cost sensitivity. Let's run J48 as is. It's building a model without cost effectiveness. Overall, all the guesses, it's 58.2% correct. Has 2 types of mistakes, false positives and false negatives, and they're evenly balanced. It includes 421 false positives and 415 false negatives. Let's use cost-sensitive classifier now. The J48 is the base classifier. This time J48 will be more careful about making a particular mistake. The two types of incorrect guesses won't be nearly the same. Overall, it's actually making 2% more mistakes now because it's taking cost effectiveness into account, and that's something we try to improve. But much more importantly, highly consequential mistakes drop from 421 to 48. To the CIO and CFO's delight, that's 9 times less cost. This is what class balance looks like. It's sample data with an equal number of examples of both types of outcomes. Often, real-world samples are not as equally balanced by class and contain a majority and minority class. One thing you'll consider is that a model will be biased if the classifier learns too much about the majority class, which messes up a fair odds ratio. Let's see in Weka a class imbalance technique. Or should I say, let's see another. You actually saw one of the ways to address class imbalance, algorithmically. Cost-sensitive classifier, which we just saw, or metacost are examples of algorithmic-based methods you may use. Let's now see a pre-algorithmic and popular way to compensate for class imbalance, undersampling and oversampling the data. These are different sampling approaches. Here's an unbalanced R file. Attributes are all numeric values. We're using them to classify active or inactive. Active is a very rare outcome. Slightly more than 1.4% of the sample data for one outcome, nearly 98.6% of sample data for the other outcome. Let's start with resample. This changes the sample size. If we make it 50, it could remove half the samples, but in itself that doesn't compensate for class imbalance. We started with 856 samples and have 428 now, but it's still imbalanced. It just randomly took half the samples, but using bias to uniform class will take a less random subsample. Here specifically say, I don't want an imbalanced data set anymore. Try to change this into a uniform data set where each class has equal samples. Since slightly over 1.4% are the minority class, I'll just put the sample size to 2.8% and see what it can do. 14 to 9. There are less samples now, but about 3 to 2 proportion and a near class balance. This time I significantly undersampled the majority class. There are also times you want to oversample the minority class, which we'll see now with SMOTE. Oversampling 100% will double the sample size of the minority class. Starting with those 12 samples, SMOTE would create 12 synthetic instances, giving us 24. Let's do 200%, which will add 2 times the samples, giving us 3 times the samples we started with. Nearest neighbor defaults to 5, and nearest neighbor is how SMOTE works. For each of the 12 minority instances, SMOTE searches for 5 of the most similar instances also in the minority class. Then it randomly picks one of those 5 to make a new instance. That's what's meant by synthetic instance. What's meant by 5 most similar is the 5 with the smallest Euclidean distance. So what contrasts SMOTE from simple oversampling is nearest neighbor. Sometimes you'd use more than one sampling technique when pre-processing. Let's say you use the spread subsample technique to reduce the data set to make it higher quality, then say you oversample the reduced data set with SMOTE to compensate for class imbalance. That's section 4, just a quick demo of class imbalance and cost effectiveness learning in Weka. And most of the first 4 sections have been about pre-processing to create higher quality input data. Section 5 will be about the processing itself. A quick quick demo of several machine learning classifiers in Weka that are popular for text classification and other data analysis too. I'll start from scratch now and breeze through the text directory loader, string to word vector, and attribute selection tools. This time, though, we're not going to use all 2000 movie reviews. Let's split it up into two R files this time, using one R file that trains classifiers to build predictive models, and an independent R file just for realistically testing the predictive models. Section 5, Classifiers. We wouldn't build a classifier using all the samples. We'd preserve some samples for validation. This time let's use text directory loader to create an R file with 2/3 of the reviews, or 1,334 samples, and create a second R file with the other third of the reviews, two identically formatted R files. To the classifiers and the models they build, the testing dataset serves as never-before-seen data and simulates predicting reviewer sentiment in the future. 2/3 to 1/3, 3/4 to 1/4, 4/5 to 1/5, whatever. You'll have your favorite rule of thumb for splitting training and testing data, and make exceptions when needed. Let's create 6 folders, 2 main folders, 4 subfolders. Let's put 2/3 of the positive and negative reviews in the train folder to build models. Let's preserve 1/3 of the positive and negative reviews in the test folder to keep aside, just for validating models. In text directory loader, to create the first R file, we'll find the train folder and save it to Weka's data folder as train.arf. And that's it. It's saved on my laptop and would open in Weka. We then create the testing ARF the same way. Assuming our training data is big enough to fairly represent the IMDb movie review population, we'd effectively be able to test models during training with cross-validation, such as tenfold cross-validation. And this way, hopefully, when we have a training model we think is good and want to validate it with the never-before-seen, kept aside, and who knows what's in their testing data set, we won't be disappointed. Naive Bayes. For each of these words, Naive Bayes assigns a probability score to both types of reviews that contrasts how discriminative, or lack thereof, each word probably is. If they're far apart, it will be used in the equation, but that word has little impact. Alternatively, if they're far apart, it has more impact on which guess is made. When next month's movie review is fed to this classifier for a prediction, Naive Bayes is going to use the words in the review and compare the individual probabilities from this side and the individual probabilities from this side. The most probable class is guessed. Each word was scored in and of itself, and learning attributes independently is what naive refers to. It doesn't care how this word is related to this word or that word or this word. It learns about each attribute independently. It says, I don't learn how these 1,000 words relate to each other. For example, I don't care if thank and you frequently appear next to each other. I just learn how discriminative the word thank is for sorting this document. I just learned how discriminative the word you is for sorting this document. When I'm asked to sort a document containing those two words, I give one a score like 10 and 5, I give another a score like 2.2 and 2.1, they simply go in the equation, finished. Using words as independent features makes Naive Bayes computationally efficient. It's nonetheless relatively accurate and good at supervised learning. Naive Bayes performs well in many different data types. For example, your spam filter may be using it. When I think of Naive Bayes, the first thing that jumps to mind is a fast way to build models for high-dimensional datasets. High-dimensional has many more columns than rows. 50, 500, 5,000 more times attribute columns than instance rows. Those arbitrary numbers make the point sometimes, such as analyzing medical data, there will need to be at minimum several dozens and sometimes thousands times more attributes than instances. Since Naive Bayes judges attributes independently and accurately, it may be an efficient choice. Multinomial Naive Bayes. This is a specialized version of Naive Bayes for text classification problems. Some consider it the standard Naive Bayes text classifier. What you might do at this point is compare pre-processing tools and classifiers, some with stemming, some without, some with word frequency, some with word present, some with stop words, some without, some in Naive Bayes, some in multinomial Naive Bayes, identifying the couple configurations that are a few percent more correct than the others were. K nearest neighbor. As far as the underlying math in all these classifiers goes, K nearest neighbor is similar to Naive Bayes, and that despite its simplicity, it's relatively accurate. Nearest neighbor takes a group and finds who's most similar. Think of the street you live on. The family across the street with a couple and teenage daughter may be most similar to the house a block away with a couple and teenage daughter. The college student a block away in the apartment complex, maybe most similar to a college student in the apartment complex 3 blocks away. That's k equals 1. If k equals 5, the college student may be paired with the college student a block away, 2 other college students 3 blocks away, and 2 other college students 5 blocks away. Let's say the neighborhood's half a mile, and all the homes in that area, we assign 5 nearest neighbors to the college student, 5 nearest neighbors to the family across the street. Nearest neighbors for prediction means next week, when a stranger moves to the neighborhood, if we want to predict if they're religious or not, we turn to the new neighbors, 5 nearest neighbors. Are more of them religious? So if 5 are not religious, or 4 are not religious, or 3 are not religious, then that's how we'll classify them. If 5 are religious, 4 are religious, 3 are religious, that's the guess we'll make. Here neighbors are IMDb movie reviews. We can set neighbors here to 5, identifying 5 most similar reviews to review 1, 5 most similar reviews to review 2, 5 most similar reviews to review 3. These are 4 different ways of defining nearest neighbor, what constitutes similarity. By default, all 4 use this same distance function, Euclidean distance. Here we can try Manhattan distance or another if we wanted, and you'll try assigning weights to specific attributes, assigning weights to specific instances, and be changing the way this classifier learns to make its prediction. J48. This is a decision tree, another popular choice for text classification, performs very well, and as you see, it's easy to interpret. Now, imagine J48 tomorrow is speaking to the 2001 movie review as it classifies it. J48 says, hello, I'm going to guess if you're positive or negative. Is the word WAST in this? Data says, nope. Too bad, almost definitely would have got that right. I'm not going to guess yet. Is the word stupid in it? Data says, nope. Too bad, almost definitely would have got that right too. Still not ready to guess. Worst in it? Data says, yep. Good, go down there. Follow this third line. So you said the word worst is in this review, right? Data says, yep. Okay, is pulp in this by any chance? Data says, yep. Alright, go down there. Follow the line. Because most of the time, if the word worst is in a review, I'll guess negative. But when the words worst and pulp appear in a review, I guess it's positive. Positive, my final prediction. And we see in parentheses 9 times it was guessed, 8 times correct. More importantly, why did J48 make these decisions? At the moment, J48 considers the presence of the word WAST as the best first question to ask. All else follows. It all starts with that first question, which of course may change after you give it more reviews, but currently J48 starts its decision making with the WAST attribute, which splits the data less 240 reviews WAST is in. Then it considers the presence of the word stupid as the next best question to ask, makes a decision on those reviews, which further splits the data less 219 reviews stupid is in, and it keeps splitting the data. Before J48 asks any questions, all it sees is randomness, or more precisely, entropy. Think of randomness as a starting point for J48 as it moves down the tree. Questions J48 asks, as when it asks them, began with WASP because in past reviews this attribute provided the most discriminatory effect. J48 likes values with high information gain. Attributes have values too, and J48 also likes values that are clear and unambiguous sorting mechanisms. J48 did 2 calculations for an information gain ratio. First, it asks, what's the average information value of all these attributes? Let's say for all these words, average information value is 0.55. Second, for comparison, it asks, how informative is each individual attribute? WASP may provide 0.88 information. When I think of J48, I think of an impressive balance of speed and accuracy. J48 is based on the C4.5 algorithm, an open source Java version. Its results should be the same. You can use pruning to simplify the classifier, and other methods to improve this decision tree learner. Random forest. This is decision tree learning as well. Forest, as in many individual trees, are used. Random, as in the trees are built differently. Each tree uses random samples and random features. That is, trees neither use all the instances nor all the attributes. The first part you'll hear referred to as bagging. We'll select how many trees to build here. Let's hypothetically build 500 trees. We can select how many attributes each tree uses here. Let's hypothetically set each tree to randomly take 100 of the attributes. And to make its prediction, random forest combines the predictions of the individual trees. In random forest for classification problems, that means each individual tree makes a categorical guess, and whichever category has the most guesses is predicted. In random forest for regression problems, that means each individual tree guesses a number, and the average of the guessed numbers is predicted. Here I use 10 trees and accuracy 72.6. When I used 50 trees, took a little longer and the accuracy went up to 77.45. When I used 500 trees, took a lot longer but the accuracy went up to 81.75. Using a lot of trees is good for predictive power, and especially so when there are a lot of instances. And we'd find a point where computational cost of adding trees is not justified by predictive power. When I think of random forest, exceptionally high accuracy is the first thing that jumps to my mind. And many a data mining competition has been won with random forest. After its high accuracy, next I think of how well it can handle overfitting, traditionally problematic for decision trees. Let's now move to the last type of classifier in this tutorial, the powerful support vector machine. SMO, or support vector machine. The last popular learner in text classification we'll see is a support vector classifier. As naive Bayes, k-nearest neighbor, J48, and random forest, support vector machine performs well in more than text classification problems. Support vector machine classifiers can be effective choices to categorize images, for example. What does this powerful algorithm do? Think of SMO less as a classifier and more as optimization techniques. Specialized techniques, such as replacing missing values, changing categorical data to binary data, a way of normalizing attributes, techniques particularly designed to improve support vector models. Support vector models are able to use kernel methods, ways of finding patterns. Here I could change the default kernel method, say to RBF. Under SMO you'll see SMO Reg, which is grayed out here for a reason I'll explain. SMO Reg is another support vector model. The Reg is for regression, as in this is a version of support vector machine for regression. SMO can improve support vector classifier models. SMO can also improve support vector regression models. When I think of support vector machine, I think of solving classification problems mostly, but maybe in this case we'd use SMO Reg to guess the number of years old a reviewer is. Regression guesses numbers, classifiers guess categories, and based on the class attribute it's clear to Weka we're trying to sort the reviews. Thus SMO Reg is grayed out based on the dataset. Weka contains different versions of similar models. Support vector machine in this case. Support vector machine can win data mining competitions as well, and while there's no classifier above all, there's no discussion about the best classifiers without it. The first thing that jumps to mind when I think of support vector machine is remarkable binary classification, when there are two classes. As the other 5 classifiers, how it works has complexities, but comparatively support vector machine is more complex than aforementioned classifiers, less easy to do right, and even scratching the surface would go beyond the introductory scope of this tutorial. This video showed a little bit about supervised learning, and there are 3 types of learning you can use. When 100% of the samples are labeled, here 2000 reviews as positive or negative, it's supervised learning. Supervised learning is most of data mining. When some of the samples are labeled, typically a small amount of labeled training data and the rest unlabeled training data, it's semi-supervised learning. If none of the samples are labeled, it's unsupervised learning. Clustering algorithms are used for unsupervised learning. By not labeling the data and not telling the clustering algorithm what to focus on, it will find different patterns in your dataset. Part of the machine learning and statistics mindset is finding new and stronger patterns to work off of. Exploring your input data, you may feed unlabeled input data to clustering algorithms. You're saying, I'm building a classifier and I have some strong patterns to work off of, but I could use some more. I use k-means here to put them in 5 groups. Clustering would not be singularly focused on learning how other attributes relate to the class attribute. And by grouping it the way it does, it's going to find different patterns. You have to label these 5 pattern-based groups. In the process, you may find a strong pattern to design better input data for learning classifiers, so also give clustering a shot. This 5-section tutorial showed some of Weka's many classifiers and pre-processing tools for text classification and certainly other types of data analysis as well. This demo was made with first-time and beginner Weka users in mind. I hope it provides them a few things which make comprehending Weka easier and faster. Have fun using Weka. Thanks.